Hello, everyone. Last physics project of the semester. The months have definitely flown by. I decided to do something fun, and I went with an example from one of my favorite shows. In this scene, this character right here, the guy on the left, his name is Brett, and he punches this other astronaut guy. And the astronaut flies back into this jet thing that's on the moon. Which, cartoon physics isn't exactly accurate, but I still figured I would go with it anyways because it was pretty fun. So there's my little drawing. It's not the greatest, but I think it shows what's going on. So basically, we're going to do a couple different parts. So for part A, it says Brett punches the astronaut with a force of 1200 newtons over zero 0.5 seconds. So we're going to calculate the impulse on the punch on the astronaut. So we know that impulse equals variable j, and impulse equals force time, that's supposed to be an arrow, times time, or change in time. In our case, it's just, the 0.5 second interval. Brett was a personal trainer, so he can get a good amount of force in there. And his force was 1200 newtons times our time, which is 0.5 seconds, which gets us to an impulse of 600 newtons seconds. So now moving on, we're going to assume that this is the positive direction. I forgot to draw my little coordinate plane, but this is the y and this is the x. We're going to assume that this flying back is the positive direction, and the astronaut's mass is 75 kilograms. So we're going to write our knowns actually for this because we're getting a little bit more. So we know already that we had our impulse was 600 newtons from the previous problem. Our mass is 75 kilograms. That doesn't look like 7. We're trying to find our final velocity, which is because our astronaut starts at a stationary position. At least in this example. In the show, I think he does run at him, but to keep things simple, he's starting pretty stationary. We're trying to find this value. So we know that J is also equal to our change in momentum, which is delta P. And our delta P equals mass times delta V. Well, what is delta V? Delta V is V final minus V naught. We're going to carry the rest of the equation down here. And like I said, our V naught is 0 just for simplicity in this case. So we're going to ignore that for now because it wouldn't really matter in our equation. And now our delta P is equal to mVF. Well, if we want to solve for VF, we have to divide both sides by m to isolate it. And our equation for our final velocity they called it in the book where there was a similar example, they called it the blowback velocity because, it's a punch and he's stumbling backwards. But it's equal to delta P over m. Now we can go ahead and plug our values in. So we have our delta P, which is the same as our J, which is 600, that's supposed to be Newton seconds, over 75 kilograms. And that came out to exactly 8 meters per second is the blowback velocity there. Now I wanted to take that a little bit further, and I wanted to kind of combine it with some of the other stuff we had already learned. So we're going to go ahead and draw another little mini diagram here just to get that motion in there. So this will be our Brett. He's just kind of standing there. He's gotta have his signature hair. That's pretty terrible. And this, oh, my bad. I said the punch was delivered at a certain angle. So we're gonna say that he kind of like punched him like in the gut that way. This angle here is our theta. And we have the astronaut who just got punched is kind of like flying backwards. That's a very bad drawing. And he eventually goes and he burns up in the jet, which is our kind of final X position. So what we want to find out here. So our problem is the punch was delivered at a 55-degree angle. So we're going to underline that to the astronaut's center of gravity, which means it's going to knock him back, obviously. He flies back for 3 seconds, and he actually does in the show. I counted it out until he hits the rocket jet. At what height is the astronaut when he reaches the jet and burns up? Because unfortunately, yeah, he does burn up. Well, so for this, we're going to write our knowns, which to start out, the first known we had was our velocity. So in this case, it's going to be our initial velocity because it's right after the punch, yes, but it's the velocity that starts his kind of journey, and then wherever he is here would have been his final velocity. But we don't really need that in this problem. We had our velocity at this second, which was 8 meters per second. We have our theta, which we're going to use with our velocity in a minute. That was 55 degrees to the center of gravity. We have our t, which is time, 3 seconds. We had our, what was our last known? We know that our y initial is 0 meters. So we're just going to take it from where the astronaut starts standing to our y final, y initial. And our coordinate plane here, of course. And our last known that I actually didn't list here, I have in my separate notes, but we need the gravitational constant of the moon. So that was kind of why I wanted to do this, because it was a little bit different than the gravity on Earth. So the gravitational constant on the moon is about 1.625 meters per second. It actually depends on where you are on the moon, which is very interesting. But for the sake of this, we're just going with the general average. Meters per second squared, my bad. So knowing all of this, we can use our kinematic equation to solve for y final. So we have y final equals y naught plus v naught y t, which is why we're going to need the theta, plus, not plus. We're going to say minus here because we're keeping this a positive value. 1/2 g subscript m t squared. So now here we can take away any zeros. We know our only zero is going to be with our y naught, so we can cross that out. And I'm just going to keep it in blue to kind of separate it from the rest of this. We have our y final equals v naught y t minus 1/2 g m t squared. We don't exactly have v naught y yet. So what we need to do is we need to find v naught y, which is equal to v naught sine of theta. We know our v naught from the previous problem is 8 meters per second, and our sine of, we're going to have 55 for our theta. And that comes out to v naught y is about equal to 6.55 meters per second. Seems kind of slow, but remember we're on the moon, so, and these guys' muscles have atrophied, which is why our character Brett, who is from Earth, has, as he calls it, Earth strength. And I wish I could upload a clip, but I can't figure out how. So we're going to go back to our equation, and we're going to switch colors again, I guess. We're going to have our y final equals our 6.55 times 3. We can finally plug those in now. Minus 1/2, our GM is equal to 1.625. And then we have our t again. We have it squared. So now we have y final equals, these two came out to be 19.65 minus 1/2 times, this altogether was 14.625. So half of that was 7.3125. Or 16.65 minus 7.3125 gives us a final y value for the astronaut is going to hit the jet at about 12.3375 meters. And that should be it. Thank you so much. Have a lovely winter break